in progress.
So we will have a look at the power distribution of a system. Now, when we have a look at the power distribution through a fluid system, there are few important factors. The most important factor is the length, the diameter, which in turn is translated into flow rate. Now, if we are transferring the fluid, to the any system, and we are increasing the flow rate, we are increasing the pressure. Now, what will actually happen is this will cause the power loss and the heat generation in the pipe. I'm increasing, it's a quite a thin pipe, and I'm trying to push all the fluid, increase the flow rate. What will happen is if you do that, it will generate the heat. When it will generate the heat is a loss of energy, which means the pressure on the other end will be less and we are wasting the energy. Okay, now if you want to increase the pipe diameter, the other way of that one is you want to increase the diameter of the pipe. So if you increase the diameter of the pipe, what will actually happen is the diameter is increased, but then the speed, the one you get on the end, will be a lot less. So we need to actually get an idea about how to balance these two factors. Okay. Also, the cost will be affected as well. Okay. Now we can have the distribution, choice of distribution. The way we try to distribute the fluid from point A to point B is we want to make sure it's transferred properly. There are very little losses over the period from point A to point B. We need to make sure if we are passing the fluid through that one, the inside of the pipe or the material is not corroded, so the material doesn't corrode. Okay. Now, also we want to make sure the pipe, the material through which we are transmitting the fluid or the power should be strong enough to withhold the stresses inside the material. Okay. Now we also need to make sure that it doesn't add the debris, the particle, the excess particle into the fluid, because in the end we will have a contaminated fluid which we won't be able to use. So the material selection is important as well. Okay. We also need to make sure the type of the fluid and operating temperature. We also need to make sure like how we are transmitting the fluid. Is it going constant? The power is constant. Are we increasing and decreasing the power? If the power is increasing and decreasing, the fluid flow rate is increasing and decreasing. What will actually happen is then there is an issue with the fatigue creep. If the temperature of the fluid is very high, there are two things. One is the temperature, the melting point of the pipe. The other is the working temperature of the pipe through which we are transmitting the fluid. The working temperature of the pipe is very important. Working temperature is far lower than the melting point. It's usually 0.4 times the melting point. That's the working temperature. So if you are passing the hot fluid and the cold fluid and the hot and cold, we are actually making the material to creep. Creep is kind of the material, it's a property or the failure of the material where you are actually passing its stresses onto the material at high temperature. When we define high temperature, it's different for different material. High temperature for steel will be different than the high temperature for lead because it's related to their melting point. Also, how we are passing the fluid. Are we passing the fluid with a sudden force, uniformly increasing force, decreasing force, and so on? Or we are actually reversing the flow as well. This all will have an effect on the selection of the material for the pipe. Okay. So we need to make sure the working strength should be suitable. Working strength of the conducting material should be suitable, which is transferring the fluid from point A to B. We need to actually have a look at the mechanical stress. The stress that should be suitable mechanical stress. It should be able to understand, It should be able to withstand the vibration and everything. To avoid the losses, the interior surface should be smooth as possible. There shouldn't be any friction. Okay. It should, the size of the pipe should be certain dimension, so it should have a reasonable fluid velocity. I don't want to have like half a meter pipe diameter at the inlet and 0.1 millimeter diameter at the outlet. In that case, that will be like a water jet. And last week we did some of the question where we have the speed at a supersonic speed of the water, so that might not be reasonable. Okay, we should place the conductor pipes so they shouldn't be damaging the normal operations of the area around the pipe. We should be able to design in such a way as to minimize the vibration and shocks. Now we should, when we design that one, we should be able to use a manifold. Okay, now the size. Now this is to do with a thing called Barlow's formula. Sometimes it's also related to the formula called the hoop stress formula. So Barlow formula, okay, Barlow formula gives you the minimum wall thickness. The minimum wall thickness should be maximum wall thickness multiplied by the outer diameter of the conductor divided by the double the tensile strength. Now this is sigma, is tensile strength. Maximum wall thickness that we should be using multiplied by the OD, outer diameter of the conductor and conducting pipe. Now, sometime in a pipe, you will have a surge peak pressure where the pressure suddenly increase. Now, this can develop in a cyclic fashion where it increase and decrease every 24 hours because of the supply and demand issues or because how you're operating the pipe. Now, sometimes the mechanical stresses can also develop into the material over a period of time as well, or because of what is flowing inside the material. Okay, so there are different standards we follow. These are the German standards, DIN 2391. Yep, outer diameter thickness is given, steel grade is given. Yeah, composition, how we do that one, how we manufacture it, and surface treatment as well. So when we look at the hydraulic pipe, you need to have a look at these different standards. Now there are ASTM standards as well. There are American standards. There are British standards as well. Okay. Now, burst pressure and working pressure. Okay. Now the burst pressure is the pressure of the fluid that causes the pipe to burst. At that pressure, the pipe will burst. Now, we have a formula. Now, if we are given, we want to find out what is the formula for the burst pressure and what's the formula for the working pressure. Okay. Okay, the tensile strength of the material is given by T equals to P times D over 2S. Yeah. Now, S is the tensile stress. So these are kind of related formula. I put here stress as sigma. Here, we have the tensile stress. So this one, we got the tensile stress. Yeah, tensile stress develops due to the pressure, which is sigma. And that is a tensile strength of the material. So we got T equals P times D over 2S. If we say the PB is the burst pressure, PB PB burst pressure, we can write that one as 2 TS over D. So I actually try to make this pressure, this P, the subject. So the 2S from here can go on this side, and this D, which is up, it can come down here. We got two different type of stresses. One is the stress at which the material break, and the other stress is the stress which is a working stress, which considering the factor of safety. So for example, in case of lift, they say like maximum it's able to carry like for example 5 people in the lift, but if there are 10 people, the lift will still go up as well. So they have a kind of factor of safety. They want to make sure the lift is as safe as possible. Exactly same thing. We have working pressure, which is different than the pressure at which the material will burst. So there are two things. Working pressure is the maximum burst pressure divided by the factor of safety. Now, depending on how crucial, how important the structure is, we can increase the factor of safety. Increasing the factor of safety means we are making the material, we are making the process, we are making the equipment more safe. If there is a pressure, if there is a factor of safety of 2, it means we want the material is failing, material will fail them at 100 megapascal of stress, but we want to make sure every time material is not more than 50 megapascal stress. So that's a factor of safety of 2. You can put a factor of safety of 10, 20, 30, but doing that one means you are over engineering. When you over engineer, you use more material, you use expensive material, which means it's going to be costing a lot of money. It will increase the cost. So we need to think about different factor of safety. Now, in a normal lift, maybe they are using a factor of safety of 3. Because obviously it's a lift. But if the component is quite expensive, pricey, and is quite crucial to the whole system, for example, let's say space shuttle, they will need to use a factor of safety of more rather than 2. They might use 10, they might use 15, they might use factor of safety of 8. Because if the component fails, there might not be a person to fix that thing straight away. Okay. So factor of safety ensures the integrity, and it wants to make sure that you are under the failing stress limit of the component.
The lower the number, the higher it is.
The higher factor of safety. Yeah, 1.5 will be it's the minimum kind of thing. Minimum we take like around 2.
Yeah.
Yes. So
like NASA and space, they're normally between 1.5 and 3.
Oh yes, for something really crucial, we increase the factor of safety. We have factor of safety of 8.
Yeah.
So maybe 10. Yeah. For normal thing, for example, when they make like for example the car, they say like on the car you can maximum 5 people can sit because they have like a shocks absorber and things. But even if like 7 people sit, it's not gonna break because or 10 people sit, it's not gonna break because they put a factor of safety of more than 2 or 3. Yep. Yeah. Okay. If there is high pressure shocks in a hydraulic system, that's in a fluid system, we use a factor of safety of 10. If the pressures are above than 180 bar, factor of safety of 4 are used. If this is from 70 to 180, we use a factor of safety of 6. For factor of safety, if it's 0 to 70, we use factor of safety of 8. The reason being is this factor of safety not only increase the safety limit, but also it's actually factor in the creep or the fatigue behavior. Fatigue behavior is when something goes under cyclic loading. So if something is 0 to 70 bar, it means it might be 0 bar, then 70 bar, then it might go back to like 60, then 70 something. So its fluctuation can cause fatigue, and we actually consider that one. So it might look very strange. At low pressures, we have a high pressure factor of safety, but at high pressure, we have a low factor of safety. But this is to considering the fatigue properties as well. Okay. Now let's have a look at a numerical question. Let's say we got a pump. It produces a flow rate of 75 liters per minute. So you have liters per minute, and we assume, because it's not given, we assume that it is water. So we know the density and everything, the volume and everything of that one. Okay. It has been established the fluid velocity in a discharge line should be between 6 and 7 meters per second. So velocity is between 6 and 7 meters per second. Find the minimum and maximum pipe inside diameter that can be used. So you want to find out the inside diameter. Okay, let's have a look at that one. So if you write it down, please, the question. Liter per minute. LPM stands for liters per minute. First thing we do is we convert the liquid per, not liquid, liters per minute into meter cube per second. Now, for water, (1,000 liters is 1 meter cube. So 75 liter is, you need to divide that by 1,000, which is 0.07. 75 liters is going to be 0.075 meter cube of water. Now it's per minute. We need to do per second. So we need to divide this thing by 60 because there are 60 seconds in a minute. So we divide this by 60. Okay, and that will give you 1.25 times 10 to the minus 3 meters cube per second. Now we have a formula, flow rate. Discharge or flow rate, according to the continuity equation, we have a formula. It's area times the velocity. We do not have the area. We do have the velocity. Now the velocity is between 6 and 7.5. So I can rearrange the equation. To find the area. So area is going to be discharge divided by the velocity. So discharge by the velocity. Now I want to find the minimum area. For the minimum area, and I want to be safe. For the minimum area here, I want to use the maximum velocity. The maximum velocity is 7.5. So I will use the 7.5 velocity. I use the velocity of 7.5. and that will give me a minimum area. So discharge, I already got the discharge from here, and the velocity is in SI unit 7.5, and this will give me an answer in an SI unit, meter square. Okay, so that will give you 1.667 times 10 to the minus 4. So you get a similar answer. Now this is the minimum area. Obviously I have the area, but I need to find out the diameter. Okay, to find that one, what you need to do is you need to rearrange that one. Let me just clear the screen. You need to rearrange this thing, whatever answer you get. You need to find the diameter. You need to multiply this thing with a 4, divide that by a pi, and that will give you the diameter square. And then in the end, square root that bit, and that will give you just a diameter. So you will get an answer as 0.0145, which is 14.56. So around 14.56 millimeter. So you will get 14.56 millimeter here. That will be the diameter, the minimum diameter you will get. And this is for the maximum velocity. Now, if you want to find out the maximum, because the question is asking us to find out the minimum and the maximum pipe inside diameter. So let's find out the maximum one. For maximum, use exactly the same formula, but instead of the minimum, you put the maximum, and instead of the maximum, you put the minimum. So A maximum, the maximum area, is going to be the same formula, but discharge divided by the velocity, minimum velocity. Minimum velocity, according to the question, is 6, because the velocity is from 6 to 7.5. So you're going to put that one here. And you can find the area, maximum area. When you get the maximum area, you do exactly the same to find the diameter. You multiply this thing by a 4, and you divide by a pi, and whatever answer, just square root the answer, and that will give you the diameter. So that will give you around 16.28 or 16.29 millimeter. So here you got 16.3 millimeter, but you will get that one in meters, convert that into millimeters. So you have the minimum and the maximum diameter. Okay. Now let's have a look at the next one. Okay. Now let's have a look at that one. If we want to find the tensile stress for a certain operating pressure, so obviously based on that one, we need to choose a material. So here we got a steel tubing as an outer diameter. So outer diameter is given. So outer diameter is given. Outer diameter is around, let me just change some things. A steel tubing with an outer diameter of 30 millimeter and an inside diameter of 24 millimeter, and it's made of some kind of steel. The tensile strength of that steel is 520 megapascal. That's where it's going to fail. They're asking us to find the safe working pressure. So what is a safe working pressure? Now, it's also mentioned it's used in high pressure shock, which means we need to use a factor of safety of 10. If it's a high pressure shock, we need to use a factor of safety of 10. We also need to find the tensile strength for a pressure of 10 megapascal. So if the operating pressure is 10 megapascal, we need to find the tensile stress. Okay. Now what are these things? Okay. Now there is a tiny error. This one. This is tensile strength, so that should be 520. Yeah. So this value is 520. Okay. Inside diameter is 24. So this is okay. The 2 is here. Now where the T is the thickness. Okay. So this is the inside diameter. And that's the outer diameter. Now here, all the way. So the inside one is 24. The outer is 30. But obviously that 30, the difference between 30 and 24 is 6. You need to divide that by 2 because half goes on this side, half goes on that side. Yeah. So the thickness is 3. The thickness will be 3. So you have the thickness. We have that value. So this is 520. So if you put that value in the calculator, so you get around 130 megapascal. Because now here, if you have a look, this was in megapascal. Hence the answer is in megapascal. Now I didn't convert that 3 and 24 into meters, because thing is, if you convert that into meter, you still got the same ratio. So you don't have to convert because they cancel out anyway. So the answer here you will get is 130 megapascal. So you have 130 megapascal rather than 129.3. Now, according to the question, it says it's a high pressure shock. High pressure shock conditions, we always use a factor of safety of 10. So we need to use a factor of safety of 10. So we got like 130 megapascal. So 130 megapascal, you need to divide that by 10. And that will give you 13 megapascal. So working pressure is 13 megapascal. So let me just clear that bit. So this is 130. Let me just write that one again. So this will be 130 divided by 10. That will give you 13 megapascal. 13 megapascal is same as 130 bar. Yep. Because 1 megapascal is 10 bar. Okay. Okay, so we have just worked out the working pressure. Now we need to find out the tensile strength for an operating pressure. So we got the operating pressure, whatever value we got. Now we need to find out the tensile strength. Okay, we have the formula for the tensile strength. This formula is also known as Hooke's law formula. Okay, so this is the same formula as we learned. Where was the initial formula? Yeah, here. So we use the same formula. Yeah, or here. If you have a look, they are kind of exactly same. Instead of stress, is the S. Okay, so we are going to use the same formula. So stress is P times D over 2T. Now we need to actually convert all into proper units. If you want, you can keep it as it is. Now this 24 and this 3, yeah, 3, you can keep that one 3 as a thickness. The diameter you can keep as 24 because they are in millimeter and they millimeter, they will cancel anyway. So you put that one and you will get an answer. Let me just check an answer. Yep. Okay, any questions so far? No. Okay, now let's have a look at the next one. The most common type of pipes we actually use are the steel pipes. The reason we use steel pipe is because with the same steel, we can increase and decrease the properties. We can do the heat treatment. We can have corrosion resistant steel pipes. We can have like a food grade steel. We can have a different type high temperature steels as well. So they have a lot of advantages. One of the disadvantages of steel as compared to like a plastic tubing or the other material is its density. It's a weight. Also, if you're using steel and the pipe is of certain length, and obviously you need to put another pipe, there's a lot of issues with the fitting and so on. Now, if there's a steel and we are using the fitting for the steel, so wherever there is a fitting, either on the bend or somewhere, when you actually fit the material, because this fitting, it will be tight here. When it's tight, it will put an extra stress on the corner, on the pipe here and on the pipe here. So this result in some kind of residual stresses or inbuilt stresses into the material, which will actually decrease the working efficiency or working pressure or working stress of this steel pipe anyway. Okay. Now let's have a look. Usually, if you prefer, some of you works in MTech, fine tubes. Anyone in this class? No. Oh yes. So they develop a seamless pipe, seamless tubes, which mean these tubes are not welded, so they are seamless. These tubes can work under high pressure. They are cold drawn seamless tubes, which mean there are no kind of stresses in there and they can work. They usually do for aerospace kind of industry. They also do for some food processing industry, or mainly it's an aerospace. Bike frames. Yes, bike frames as well. Yes, expensive bike frames. Okay. Now, these are different fluid power standards and different pipes. So the normal pipe size in inch, the outer diameter of the pipe, and these are different schedules, different standards we need to meet. Schedule 40, Schedule 80, Schedule 160. And they actually give you like at least what should be the minimum internal diameter. What should be the working pressure. That pressure is in PSI, so you can do the conversion. If you have a look, as the schedule number is increasing, the wall thickness is increasing as well. So if you have a look at the wall thickness, the internal, which is the difference between the internal and the outer diameter divided by the two, yeah, it's kind of increasing. Okay. Now, okay, same thing here. So this is just in metric system. That's it. Okay. Now let's have a look at one more question. We got the ID inner diameter of 25, a steel tube with the inner diameter of 25. The burst pressure, that one, is given by 50 megapascal. The tensile strength, which is an S, is given by 380. Okay. We need to find out the inner diameter is given. We need to find out the minimum acceptable outer diameter. So, which means we can find out the thickness. If we find out the thickness, we can just work out because the inner diameter is given. So we can just work out that bit. Because this is in megapascal, 380 is in megapascal and 50 is in megapascal. It's no point converting that into pascals because they the answer, it will sort itself out anyway. Mega and mega, they will cancel. Okay, we have the formula for the bursting pressure, 2Ts over D. Now we just put the values. The value for the bursting pressure is 50 mega, and the stress was 380. We have the diameter as 25. So this is diameter, which is 25. We have the value, well, constant 2. So just rearrange and find the T. If you leave that bit, the maximum one, like as in 25, you will get an answer in millimeters. So it's up to you if you want to convert it. Now, if you rearrange that one, when you rearrange this thing, it will become 50 times 0.025 divided by 2 times 380. And that will give you the answer for the thickness. So this gives you the answer in meters, 1.65, around 1.6447. So 1.65 or 1.645 millimeter. So that will give you the answer in millimeters. So it's good not to convert this thing 0.025 into meters. Leave it in millimeter because the answer will be in millimeter. Now you need to find out the outer diameter. To find the outer diameter, now this thickness here is given. So thickness value is given to you, which is 1.644. And obviously there is another thickness here as well, which is 1.644. So to find the outer diameter, you need the inner diameter plus 2 times the thickness. So you got 25. Yeah, strangely, I got the same answer, but I made the same mistake. Yeah, what you did. Yeah. Okay, because the answer is in 10 to the minus 3. So you need to convert that one into millimeters, 1.6. Put one, yeah, because you're putting the answer as in millimeter. Yeah, and this one, I did exactly the same mistake. Yeah. So now if you put that one, you will get the value for the outer diameter. Outer diameter should be that. If you get a thickness, you can convert the thickness into outer diameter. Yeah. So 28.3 millimeter. 28.288. So 28.3. Okay. Okay, let's have a look at this one. This is a very similar kind of question we did. So if you try that one on your own, please. Okay. Now you are given, you need to find the minimum size of the pipe tubing. The wall thickness is given 2 millimeter at the inlet, and the outlet it's it's 75 lpm liters per minute. First thing you need to do is convert that liters per minute into meter cube per second. So you need to divide this 75 by 1000. That will convert into meter cube. Then divide the answer by 60. That will convert into second, meter cube per second. Now, when you got that bit, you need to actually find out the flow rate, the discharge. To find the discharge, the formula is area times the velocity. Now you have all the velocities. You have the 1.2 and 6.1. You have both velocities, 1.2 meters per second, 6.1 meters per second. You do not have the area. But you have the discharge, how fast it's going, 75 lpm. So we are going to use that equation, rearrange that one, and we find the area. Now to find the area, we can find the minimum area. We can also find the maximum area. For the minimum area, we use a maximum velocity. For the maximum area, we use the minimum velocity. Yeah. So first we need to rearrange that one to find the area. Area equals Q divided by the velocity. Discharge divided by velocity. Discharge 75 LPM. I already converted that into 1.25 times 10 to the minus 3. So I got the discharge. Now discharge is this one. Velocity I'm going to use because I want to find the minimum area. This is the minimum area. To find the minimum area, I need to use the maximum velocity. And that will give me an answer. Okay, anyone else got different answer or just me? Now, so this is 1.25 times 10 to the minus 3 divided by 6.1. So that I got answer 2.049.
Yeah, I got the same.
Yeah.
10 to the minus 4.
So this answer here, it's 2.0491 times 10 to the power minus 4. So this answer is here is incorrect. Okay. Now, when we got that one, we need to find out the diameter. So you need to multiply that answer by 4, and you need to divide this answer by pi. Whatever answer you get, you need to square root that one. And you get 0.0161.
What did you get, sorry? Yeah.
16.1 times 10 to the minus 3. So the diameter will be 16.1. 16.15, yeah.
No, do you have to find the maximum area? No. Don't do it.
Okay, so now you got that one. Okay, so we got the diameter 16.15. So that's the diameter. And the wall thickness is 2. Okay, the wall thickness is 2. 2 is the wall thickness. And we got the diameter. Okay, 16.1. Okay. Now, we need to look for 16.1 millimeter for the internal diameter. And we have a 1.14 table. Let's see if there is a table down there. Yeah. So, where is gone? Yeah. Okay. So we need to go back to the, let me just clear the screen. 1.14, 1.4 table. Yeah. So we look at where it is, and we based on that one, we can just select the outer wall. So the answers over there were incorrect. So obviously, the corresponding order will be incorrect as well. But yeah, so you can just go back to the look at table, and you can just find out the corresponding. Same again, we need to find out the maximum area. We do exactly the same bit, but for maximum area, you are going to use the minimum velocity. Yes, I think that's what they did. Yeah, 18 and 22. It should be over there. Yes. Oh, okay. That's good. So this answer 16.2, thank you, was here. So if you do that one, that should be 36.5. Yeah. Okay. Let me just write it down. Okay, now we put the same thing for the maximum area. So discharge is exactly the same, but velocity we use the minimum 1.25 minus 3 divided by 1.2. That will give you, yeah, that will give you this answer. So these two answers, this should be here, and this answer should be here. This should be, this 36 should be here, and this 16 should be there. Yep. So they put the answers incorrect. Yep. Okay. You can go back and have a look at the table, and you can just work out which one you're going to use for the inner dia and outer dia. Yeah. So you can actually straight away look from here. Yeah. What's the inner dia? What's the wall thickness? And so on. Yep. So you can straight away have a look at from which one you're going to choose. So this table, if I just do, the tables are like this. So here you go. So these are 3 tables. So outer dia, inner dia, wall thickness. So we look at what was the inner dia, outer dia, according to what we got here. Let's say the inner dia is 18. Yeah, and we can have a look at the outer dia is 22. But how come? So diameter here is 16.2. Now diameter here is 16.2. So I can have a look at 16.2. So yeah. So obviously, if I have an outer diameter at 16, the inner diameter has to be 10. But obviously, we're looking at here 16.2 outer diameter. We also need to have a look at the wall thickness. Now, what was the wall thickness here we got? The wall thickness is 2. So we need to look at the wall thickness of 2. So you can see the wall thickness of 2 is here. The wall thickness of 2 is here as well, but obviously we cannot use these values. So hence, based on that one, we will choose, it's other way around, 18 and 22. Yeah. If I got 1, obviously I can just add 4 because on the both side the wall thickness is 2, and I can choose that bit. Okay. Now let's have a look at the next one and the last one, and then we have a look. Okay. Okay, we need to figure out the commercial pipe tubing, the size of the minimum size of the commercial pipe tubing. The wall thickness is given. So the wall thickness is given as 2.4 millimeter. Okay. The flow rate is given, the Q is given as 0.00189 meter cube per second. The minimum velocity is 1.92. The maximum velocity is 6.08. So for this one, you need to actually use different values and see which one suits best. So you choose a random value from the table. Yeah. When you look at the random value from the table, you need to actually look at the value which corresponds to that 2.4 millimeter wall thickness. So you need to go to the table. You need to go back to the table and you need to actually have a look at, let me just clear the screen. You need to actually look at the wall thickness. You need to actually have a look at the where the wall thickness is 2.4. Where these you can't see 2.4, so don't choose a lower value, choose the higher value. Let's say it's 2.5. So 2.5 wall thickness is here. The wall thickness 2.5 is here as well. This one, and you got this one as well. Is there any more 2.5? No, just these two. Yeah. So we got two. Yeah. So we can choose 2.5, and I'm going to go for, let's say, inner tubing is 23 and outer is 28. So you got these value. Now you need to find out the velocity equation. Use the velocity equation. Or discharge is velocity times, you only know discharge equals velocity times the area. Or velocity is discharge over the area. Discharge is given here 0.00189 divided by the area. Area is pi over 4 d square, or you can do pi r square. The diameter here is given, which we have actually chosen from there. Inner diameter 23. We just put the inner diameter and we just work it out. So let's have a look. Let me just check the answer. 0.00189 divided by pi over 4. Multiplied by 0.023. Okay, that will give me 4.55. So 4.55 or 4.54. Let's say 4.55 meters per second. So I got the velocity. So I use that one. Now the velocity I got here is 1.9 to 6.08. So it's a little bit less than 6.08. Now, which means I can increase the thickness to, let's say, 3. If I increase the thickness to 3, that will give me, and I use a table where the thickness is 3. I look at that one. And outer diameter is 25, and inner diameter has to be 2 times outer diameter minus 2 times the thickness, which is 19. So I use the same formula. Velocity is discharge over the area. Discharge value is given. Now I need to find out the area. So that will be 19. So I change that value. That will give me 6.66. So now I need 6.08. And I was getting 4.54. Now I'm getting 6.67. So once I got low value, now I'm getting high value, which means it will not be stable. It will cause, for low value, it means we are using a pipe of higher diameter, not suitable. That means we're using a pipe of low diameter, not suitable. It will heat up, friction, we will lose a lot of power. So now let's choose and do another one. So now thickness is still 3. We choose thickness 3. Outer diameter is 42 and the inner diameter is 36. So what I'm trying to do is I'm just trying to get that number, the bottom number 0.19, a little bit bigger. If I get this number, little bit bigger number, what will actually happen is it will reduce that value. So now let's have a look. I got the discharge already. Now the diameter, inner diameter, I'm going to use 36. I put that one and I will get an answer which is 1.86. Yeah, so 1.85 or 1.86. Okay. Now 1.86, which is, if I have a look, yeah, I need 1.92. Yeah, so this will be suitable. 1.92 for the outlet, no, inlet velocity. I can choose this pipe with thickness 3, outer diameter that, inner diameter that. I can do that one. But for this one 6.67. Now then we have a look. We need 6.08. Now if we cannot find any other, we can go with that one. If there is no other pipe diameter, we can go for the one that's we actually calculated. So that difference is not that much, 6.67 and 6.08. So for the outlet we can use with 6.08, we can actually use 28, 23, 2.5. Yeah, so we can use that one. So difference is not that much. But if I use that much, you can see a difference is massive. Yep. So yeah, so here I use the thickness 3, isn't it? And here, if I have a look here, I still use the thickness 3. So if I decrease the thickness to 2.5, which will actually decrease the value, yeah, which will actually decrease these values further, and we can use that one. So we can get a little bit higher value here, and this can decrease a little bit further. Yeah, so we can have that one. Okay. Now then there are some standards we actually use. It's called Society of Automotive Engineers. Now, when we have a look at the Society of Automotive Engineers, let me show you SAE 1010. What does that actually mean? Let me, if I go to Google. Okay. Okay. Now, when we have a look at the steel composition or the standard composition, let's say it's SAE 1010. Now, the first 10 represent that it's to do with the steel. The other represent the percentage of the carbon, 0.1%, 0.2%, 0.3%, and so on. So this is how the composition of the steel. Every material is designated a number, and we work based on that number. Okay. So we got SA 1010. Now we got two different materials. SAE 1010, tensile strength is 380 megapascal, and then we got another material, AISI 4130. Now with 570 megapascal. So two standards, different material. We are given a flow rate which is 0.001 meter cube per second, and the operating pressure is 70 bar. The velocity recommended is 6.1 meters per second, and we are using a factor of safety of 8. Now, first thing we need to find out, we need to use a continuity equation. Discharge equals area time velocity. So we need to find the flow area is same as area. We find area is discharge of velocity, so we find the area. Yep. So we will get this value for the area 0.001000016 meters square. We multiply that by 4. We just rearrange that one because we find the diameter. We multiplying that by 4, dividing by a pi, and whatever answer you get, you square root the answer. And that will give you the diameter, the inside diameter, 14.45. So that will give you the inside diameter, which is 14.45 millimeter. Now we are just looking into the first part, the material with 380 megapascal tensile strength. So we have the value. Now we go back to the table, 1.4 table. Now the diameter, the inside diameter is 14. So we already calculated that one. So obviously we can't find 14.4. So what we look is, we look at one diameter less. So instead of 14.4, let's have a look on the table. We just go for the diameter, which is going to be that one, 12, one less than that. And the outer diameter is 15. So we got the outer diameter 15, inner diameter, this is from the table. Yep. And the thickness has to be 1.5 because 12 plus 2 times 1.5 is 15. Now we need to find out at what pressure, what is the pressure that it will burst? What is a safe, not safe pressure? What's this pressure it will fail? So we still doing that one. So we have an equation. Burst pressure equals 2 thickness times the tensile strength over the diameter. It's up to you if you want to convert the tensile strength. So up to you if you want to convert the tensile strength into megapascal to pascal, or you want to convert this thickness and diameter into meters. You can keep it in millimeters, still give you the same answer. So 2 times thickness is 1.5 multiplied by 380, and the diameter, inner diameter is 12. So that will give you the answer of 95 megapascal. So it's not going to be 94. This is 95 megapascal. Yeah, you have 95 megapascal as an answer. Now, once you got this burst pressure, we need to find out the working pressure. Working pressure is the value 95 we got already, divided by the factor of safety. The factor of safety is given in the question. So that will give you 11.8 or 11.9. So that will give you 11 point, let's say I round out to 1 decimal place. So that will be 11.9 megapascal or 109 bar. But the working pressure over there was given as 70 bar. Now working pressure here is like around 120 bar, 119 bar. So which means we can choose that this will be saved because the working pressure is 70 and this can work up to 120 bar. So I can use this pipe. Okay. Now let's say if I want to do the next one, next material. Exactly the same one. Now the only thing that will change here is the strength. So strength here is 570. Yeah. So this is not 517. It is 570. And that will give you 142.5. So we got 142.5. Now we use that 142.5 and we divide this by 8. That's wrong. That is wrong. So that will divide by 8 will give us 17. So that will give us around 17. So this should be, let me just pick this one up. That should be here. And that should give you an answer of 17.8. is megapascal is 178 bar. So which means it's still safe to use that pipe. Yeah. Even though the factor of safety is kind of not 8, it will be for hit double, but we can still use that pipe. Yeah. This pipe can be used. Okay, I will just save this one and